Hello, my name is Anusha. I am a machine learning engineer with around 3 years of experience. I am passionate about knowledge graphs and AI agents, and this was an ideal opportunity to explore solutions combining their strengths. The dataset I have used is the Gowalla location-based social networks data. This dataset had two files. One file contained check-in data with user ID, check-in time, latitude and longitude of the location, and the location ID. The second file contained edge data of the friendship network in the form of user ID to user ID tuples. I also augmented the location data using nominatim to fetch information such as the state, city, county, neighborhood, road, type, class, and amenity. And I also used Google search to search the amenities and extract search snippets. This is the Jupyter notebook where I implemented the application. I first started by loading all the data. I loaded the check-in data and extracted unique locations. I filtered the locations for locations within New York City. I then augmented the location data using the nominatim API. I then followed by filtering the user IDs for users who have visited locations in New York City, and then I loaded the friendship network data. I also augmented the location data by fetching snippets, search snippets of the amenities from the Google Search API. I then created the knowledge graph in Network X. I started by creating the user nodes, followed by the location nodes. I then added the attributes fetched from the nominatim API to the location nodes, and then I created an edge between the user and location nodes. I then created edges and nodes between the additional information fetched from nominatim about the locations. And I created the friendship edges between the users. I then saved the graph as a pickle object to load for later. Here is a visualization of the subgraph. This is a location node connected to different things such as type, neighborhood, class, road, county. The location node is connected to a user, and the user is friends with two other users, as shown in the graph. I then implement a graph neural network over the graph, specifically the message passing algorithm. I generate embeddings for the amenities using the amenity search snippets and OpenAI embeddings. For all the other nodes in the graph, I use a vector of zeros as the initial embeddings. Here I implement the message passing algorithm. This algorithm takes an average of the node's neighbors' embeddings and then performs a weighted average over this result and the node's original embeddings. This process is continued for t time steps in a loop. I then persist the graph using ArangoDB. I use ArangoDB and NetworkX client and use this function to load the NetworkX graph into ArangoDB. This section sets up the agents and the tools. I start by loading all the required data and objects so that I can run this section independently. I create an extensive description of the graph schema, such as the properties the nodes and the edges have, and the values that those properties can take. This tool generates AQL to execute over the RangoDB database. I add some AQL examples relevant to my graph and also add a few additional lines to the prompt, specifying that the graph is an undirected graph. This tool generates code using the NetworkX library. I also implement a loop which on error passes the error message to the LLM and asks the LLM to regenerate the code. I use a conversation chain with memory for this so that the LLM remembers its previous output. The result of the code execution is sent to the LLM again, and the LLM formulates the final response. I also create a new tool to search for points of interest. This tool loads the amenities initial embeddings into a vector database and performs a search over this database using a textual query. The LLM can also pass a list of node IDs to the tool, and the tool searches for a result which is a subset of this list of IDs. I also implement another new tool which takes an input node ID and recommends a similar node based on the learned node embeddings from the message passing algorithm. This tool also takes filters in the form of IDs to include in the results, IDs to exclude in the results, and the node type that the results should have. The similarity is calculated using the cosine similarity, and based on the filters, the relevant indices in the similarity vector is set to a -2, which is lower than the minimum result of the cosine similarity function. If the maximum similarity is less than -1, then the tool returns that no results have been found. Here I initialize the React agent and pass it all the relevant tools, and also add a few more sentences to the prompt. This function takes the query and the answer from the React agent function and then uses an LLM to generate NetworkX code which visualizes the answer. Here are some of the queries I have run using the agent. For this query, the agent uses the point of interest search tool and performs a simple vector search over the amenities embeddings. This query combines the point of interest search tool with the AQL tool, where the AQL is used to find the IDs of the amenities in Bergen County, and then those amenities are searched with the query of for donuts. These queries demonstrate the use of the similarity search tool. These two queries are a simple use of the tool using an ID without any additional filters. So for this result, we get another user, and for this result, we get the location which the amenity is connected to. This query combines the similarity search tool with the AQL tool, where the AQL is used to find the IDs of locations which have been visited by user 0. These IDs are then passed as the exclude IDs to the similarity search tool, and the node type we are seeking is location. This is a similar query where we are searching for new friends for a user. These queries are simple degree calculating queries. This query counts the neighbors of a user where the neighbor is also of a node type user and finds users which have exactly 50 friends. This query finds the user with the most number of friends. This query calculates the number of location node neighbors a user has and then calculates an average of that number of location neighbors using network X. This is a simple path matching query where we find the amenities visited by user 0. The amenities are connected to a user using a location node which acts like a bridge between them. Here we also visualize the results. Since the location nodes include latitude and longitude coordinates, we can use this information to extract insights from the graph. This query finds the two most distant places user 0 has visited using network X code. We can also leverage the time-based information. This query finds the first and last locations that user 0 has visited. The agent can also answer graph algorithm-based queries such as the shortest path between two users, the most influential user using degree centrality. The agent can also answer queries combining simple graph queries with complex graph algorithms such as who is the most influential friend of user 3401. Here is a real-time demonstration. This query uses the similarity search tool and the AQL tool to find a new amenity to recommend to user 0 which they have not already visited. This query performs a simple path search and finds amenities that are visited by user 0. Amenities and users are connected via location nodes. Here we also have a visualization of the result. The user is connected to location nodes and the location nodes is connected to amenities. This query leverages the latitude and longitude coordinates to find the two most distant places that a user has visited. Here we also have a visualization between the user and the locations. This query finds the shortest path between two users. We also have a visualization of the shortest path.